Hello and welcome to this Automation Academy Mastering the Machine webinar from September 16th, 2023. And the topic today was PLC philosophy. This is a repeat of the webinar that I did for control engineering on September the 14th, which was September the 14th, which was a Wednesday. So I covered many of the same topics, but in a little bit different way. I hope you enjoy it. Good morning, ladies and gents, and welcome to yet another Mastering the Machine webinar, this one for 16 September 2023. And the topic today is PLC philosophy. This is actually extracted from a webinar that I did this week on Wednesday for Control Engineering Magazine. So I'm going to be using the same slides, but approaching it from a little different direction than I did during that webinar, maybe expounding on some things I mentioned there. If you want to check that out, I don't have the actual link for it, but if you go to Control Engineering Magazine, I think it's controlengineering.com, I believe, you should find a copy of that webinar. And it was about an hour long, and I think a couple hundred people attended, which is a lot more than usually attend my Mastering the Machine webinars. So it was pretty interesting stuff. We'll get the basics out of the way here. This is sponsored by the Automation Academy, which is my membership site. On the Automation Academy are training videos for Allen Bradley, Siemens, Beckhoff, Omron, which is actually the platforms we will be talking about today. There is some information there on job and aptitude assistance extracted from kencoleman.com. Lots of systems integration topics, things like that. There is a library of training and technical documents, some software on there, including some PLC programming software. Community with interest groups, not a lot of attendance there, called IO Central. You can find that at community.automationllc.com. And we do have these regular events every 2 to 3 weeks or so. So without any further ado, I will be entering into the control engineering webinar, which again, I did this last Wednesday. And one of the things that's going to be a little different about this webinar, they're pretty particular about not advertising specific platforms. So everything you see in here is going to say platform A, platform B, platform C, platform D. And I kind of hinted in that webinar, you should be able to guess what the platform is just by some of the names used that I did in there. But anyway, so this was the little blurb that they had for me. People could earn these RCEP credits. They got 1 hour of credits if they completed an exam. And I actually created the little questions for that exam. And I don't know if you can go there later and watch the same webinar and get the same credit or not. But anyway, so I titled this PLC philosophy, whereas their title had something a little different on it. It was about templates and things like that. So I started out talking about history, and this is the core of why so many of these platforms are different. And I kind of gave the basics here. Some of this is in my book. Speaking of which, I want to announce something else here real quick. Everybody that's kind of followed what I've done, I've published 3 or 4 books, including a book called Advanced PLC Hardware and Programming. And then I went back and republished an older book called PLC Hardware and Programming Multi-Platform. And I rebranded it for Automation NTH. And I realized when I did that, they needed it for Dexcom, which is one of their customers. And Dexcom kind of requires that book for their training. But I didn't have the platform-specific material in the multi-platform book. So I created a new book. This book, again, will be available, Barnes & Noble, things like that, mid-October. And this is going to be a pretty different book. It is a companion book to the basic book, but it saves you a lot of money if you get this book instead of the Advanced PLC Hardware and Programming book if you are concentrating on Allen Bradley. There is no Siemens material in there. It's all AB, and I did put a lot of extra material in there, some AOIs that I use, lots and lots of code examples. So it's really a pretty advanced book, probably even more advanced than my advanced PLC hardware and programming book. And we're going to be using this for the NTH University classes. So this is the cover. It should be out mid-October. So that's kind of big news for me. I'll be getting those, probably be getting about 10 copies to start with for myself, but you can get those on Barnes and Noble and Amazon, all the normal places you get books. So it will be called just PLC Hardware and Programming, Alan Bradley. So if you're interested in Alan Bradley platforms, which is one of the things we're going to talk about today. Okay, so early computers used groups of 4 bits, and I looked a lot of this up on Wikipedia and things like that, just to see what the history of some of the earliest computers were. And that's where the 4-bit stuff came from. So nibbles and hexadecimal and all the things that you may know about already. But that's how data was encoded from pretty early times. And then the 8-bit microprocessor, notice it's a multiple of 4, was developed in the 1970s, and it popularized the use of the byte. And that's where some of the platforms got their byte-based programming as a data storage size. And early relay logic was designed by hand drawing circuits. And this was kind of when I got started at it. I used to hand draw my code, and then I used to have to convert it into mnemonics to enter it using a handheld controller. So that's how stuff was done in the late 1980s, early 1990s. We didn't have laptops. You had to draw the circuit out and then convert it into mnemonics, test it, make sure that it worked. And so when I say entered using proprietary programming terminals, each of those terminals, it was not like a laptop. You didn't run software on it. You plugged it into the port and programmed it that way. Or sometimes they had these giant CRTs on carts. Alan Bradley in particular had that. First PLC, I've mentioned this before, 1968. It actually was fabricated in 1969, but they won the contract to build it in 1968, and that was Modicon. I can mention brands here. So programs were stored on magnetic tape. Non-volatile magnetic core memory was used for processing, and I actually have some more information about that in my maintenance and troubleshooting book. I talk about how core memory works and how they magnetized all those little coils and kept non-volatile memory there, which is very interesting also. Anyway, modern PLCs evolved from those original formats, and everybody took slightly different directions. So this is just a picture of ladder logic. This is an example of something that might have been probably not hand-drawn, but created by some kind of a CAD program. And then you would convert this to mnemonics, load A and B or C or something like that. In the 1990s, PLCs came to be programmed with software and PCs, and that's kind of where we are today, right? Everything's done with a laptop. Microprocessors evolved to 16-bit microprocessors. We were no longer in the DOS age. And things started migrating to Windows. Still, everything's pretty much programmed with Microsoft. And in 1994, IEC 61131 defined a standard and said, this is what PLCs are going to be. This is the data types they're going to use, that sort of thing. This is what the instructions will look like. And it immediately made all PLCs non-compliant. Right when that happened, there were no PLCs that followed all of those rules. A big reason for this was that they were 16-bit. Timers had to be 16-bit. A lot of the timers timed down instead of timing up. That's not compliant with IEC. Some of the timers had time bases. Time bases are not compliant with IEC either. So you've probably done Alan Bradley programming where you have to put in 100 millisecond time base or 1 second time base or whatever. The longer your set point is, the bigger time base you have to use. And the reason was you had to squeeze the number capability into a 16-bit number, which only goes to, there's 65,536 values, but only half of those are positive. And most companies used signed integers. So that's where all that came from. So that's kind of how they evolved. And why does this matter? Because from that point, the PLC platforms that had been created evolved in different ways. Some of them were byte-based, some of them were word-based. And PLC platform recommendations, which was the core of why I did this webinar. They wanted to define some standards and things like that. And I kind of turned it into a little different take on it. I said, you know, all PLCs are still a little bit different. And certainly the older PLCs, the non-compliant ones, which are still out there, are you can't write a single standard easily for all of those PLCs. So we're going to talk about a little bit of why here. Platform recommendations, languages, and styles are also going to depend on the region you're in and your industry. So here in the United States, we use a ton of ladder logic, and people wonder sometimes why. If you go over to Europe, they use a lot of statement list, for instance, in Siemens, and then a lot of younger folks want to use structured text. And I'm going to address some of those things today and why that may or may not be a good idea. So the case study that I did here, I called them platforms A, B, C, and D. A, you know, kind of easy to guess what it is. It's Allen Bradley, A for Allen Bradley, right? B, I made Beckhoff. C is actually Siemens. And D, I've done Omron classes lately, so I threw a Japanese PLC in there. And Omron was actually my first platform that I went to school for in the early 90s, went down to Atlanta and went to all their training classes. And at that time, Omron was programmed with DOS. You had DOS software and you had handheld controllers, and we would have to turn the code into the mnemonics that you would type in with the handhelds and that sort of thing. A blank screen. That's interesting. Okay, so case study. A, C, and D. I'm not mentioning B here because B is Beckhoff, and Beckhoff did not have an older registered-based platform. Beckhoff is a computer, so you had to have a laptop. It was not programmed with handheld controllers, and there really is no older version. There is a TwinCat 2 version, and I assume there's even maybe a TwinCat 1. I don't know what that is, but it probably wasn't register-based. It was probably still tag-based or name-based programming. So between A, C, and D, which again, A is Allen Bradley, C is Siemens, D is Omron. So here's some of the differences. A is 16-bit word-based. So if you've ever seen the integer registers, that's kind of the core of everything, right? N7 colon something would have 16 bits, and the addresses would be N7 colon 1/0 through /15. So their numbering system would follow that nomenclature. All of the registers in these older platforms, Allen Bradley, SLC, and Micrologix, are retentive. You don't have to worry about that. Another huge difference is I can look at a saved copy of the program and I can see the values in the registers. So all the registers are retentive, and when you save a program, those numbers are still in there and you can see them. The registers are by data type. Again, on that older platform, you had N7 for integers. You could make any other N you wanted to. You had B's for bits, and you could combine the bits into words. There was B3 colon 2, and it could be kind of treated as a word, but you couldn't do a lot of math with it. It had, you were meant to use those as bits, like B3 colon 2/0/1/2, that sort of thing. So different numbering system there. They used programs and routines. In the older platform, there is only one program. So the program is just whatever you save. They didn't call it a project. And then you had routines within it. You started with the first routine, the main routine, which was ladder 2, different name than everybody else used. You could only program that in ladder logic. However, instruction list is available. If you ever double click on your rung in Allen Bradley, you will get the text equivalent of your ladder logic. It will appear at the top. And so ladder is the main program platform there, even though the mnemonics are back there and instruction list is there. So only 2 of the 5 IEC 61131 languages are there. Global memory, everything was global. You have integers and bits and floating points and whatever, and everything was just a great big old set of registers, and any routine could use those. So kind of basic when you think about it. Now, when you get to platform C, which is Siemens, it's in the same era. They had an S5 and then they came out with an S7 very much based on the same kind of platform. Everything is byte based. So all of your addressing, you will not see anything higher than .7. It's, M10.0 through M10.7. You only get 8 bits per byte. And if you want to make a word, you have to combine 2 bytes. If you want to make a double word, you have to combine 4 bytes. And so that affects everything about that platform. You really have to understand the octal addressing. You really have to understand how their data blocks are built. Data blocks are something that wasn't available, of course, on platform A. So that's another very unique thing. The retentivity, the M bits were assignable. And by default, only the first 16 registers in the S7 platform are retentive. So if you have a memory word 50, memory word 50 is not retentive unless you choose to go into the hardware settings and make it retentive. That can be very disrupting, because if you download a program and you have data saved in there, it's all going to go to zeros. It's not going to be retained at all. If you do a download, it's all going to be zeros, unless you saved your program by copying the state of the registers from the online version into the offline version. But you had no way to view it. So you couldn't save the program, open up the saved program and see what numbers in which registers. It just wasn't there. Still isn't there to this day. So this is the S7 platform, S7 300s, 400s, 200s to a degree. That's very obsolete, but the 300s and 400s are still out there. They use things called organization blocks. Doesn't exist at all in platform A, which is Allen Bradley. That is a pretty special thing, because that's how Siemens addresses its fault issues, processor errors, things like that. If you have the correct OBs, or organization block, in your processor, you can literally make it bulletproof. It will not stop running, even if you have programming errors, even if you have memory overruns, even if you lose IO and things like that, unlike Allen Bradley. They used functions and function blocks, which are a kind of a standard new programming, modern programming technique. Allen Bradley did not have this in platform A. They did come up with it in the newer tag-based systems. They do have the equivalent of function blocks, but we'll talk about what the difference is there. They have all languages in Siemens. Ladder and instruction list, which is statement list, that's super instruction list for Siemens, is dominant. So if you go to Europe, they wonder why we use ladder here. Well, we use ladder because that's how Allen Bradley evolved, and that's probably over 50% of the PLCs in the US. So that's why people use ladder here. You go to Germany and talk to some of the programmers, they actually learned statement list first in college. So they have a lot more rigorous programming training than we have here. Things are a little bit haphazard as far as PLC training in the US. It's mostly paid for by the vendor. The schools don't have great PLC programming classes, especially in ladder, right? Because the instructors haven't practiced with it for 30 years or whatever. So statement list is dominant in platform C, but ladder is used some. But they do have function block diagram. They have SFC, things like that. They have both global and local memory. You can put your tags in the M words. You can put them in data blocks. You can make your data blocks private to a specific routine, and you can use UDTs. So that's a modern thing defined in IEC 61131 that was not available in the Allen Bradley project of the same era. So that's interesting. D, platform D, and I'm not an expert on platform D, but I've taught a couple classes in it recently. 16-bit word base, so everything is .0 through .16 kind of, or .15 kind of thing. The retentivity is very interesting in Omron. It is register based, so your W bits, you have a lot of what they call working memory. Working memory is not retentive. Even if you turn off your processor, turn it back on, the numbers in the W registers will be gone. So if you want to make your things like auto and manual mode is one of those particular things, you'll latch that in usually and stay in manual mode. And if you power down the processor and come back up, you want certain things to be retained. Well, you better put them in the H registers, which are the holding registers. for Omron. And they have a whole lot of other registers. They have task registers. They have A registers, which usually have something to do with the processor, kind of like the OBs in Siemens, right? They have different registers for different purposes. I want to say probably 9 different types of registers there. And it's by function, not by data type. So you can put words and bits and things like that in all those. Usually the words end up in the D memory, which are just a big list of word registers. They use tasks, programs, and sections. So you can have multiple programs running, and they can be somewhat private. So I said global memory and UDTs, but you can kind of make things private to a particular task or program. Again, it's not my main platform, so you'll have to look into that a little more yourself. The programs can be assigned to the tasks, and I believe you can have 16 tasks. So that's kind of like having 16 programs. And then sections are really not like routines, but they're sort of like chapters of a book. You can jump from section to section, and it sort of looks like a routine, but it'll all be in the same program or the same task. All languages are available. Like I said, when I first learned Omron, it was an older platform, the C200Hs and CV series. We did everything in ladder and instruction list, but now on that older, which is now it's the NJs and things like that, still tag based, but all languages are available. They do have UDTs, so they've adopted some of the things from IEC 61131. So this is a little bit of what the product looks like there. That's the ladder logic equivalent in all these. So notice there's B's, N's, and I's and O's in platform A, which is Allen Bradley. You go to Siemens, it's M, which is general memory. You have DBs, data blocks, doesn't exist in Allen Bradley. And then you have I's and Q's instead of I's and O's. And then here is something from Omron, and W addresses. You can barely see them here, W23.00. That's a permissive, and that's non-retentive. So H is retentive. And then they use X's and Y's, but honestly, you won't even see the X's and Y's most of the time. You'll just give it a tag name. And unless you expressly say, I want to view those registers like are here, you won't even see those. You'll just see the tag name or the symbol equivalent. All right, modern platforms. So I did A, B, and C here. I kind of dropped Omron out because I don't know much about Omron's tag-based system. They do have one, and I assume it's just IEC compliant like all of them are nowadays. Again, Allen Bradley, they use tasks, programs, and routines. You can have multiple tasks, but you can only have one continuous task. So where Omron had 16 different tasks, they were really programs as far as Allen Bradley is concerned. So different names. Routines are what they call it in Allen Bradley. That is just a selection of code. And then you would call all of your routines from your program. You can have both global and program tags, but you can't have, I would call it a routine defined tag, which the difference between platform C, which is Siemens, is you can have a FC, which is a subroutine, and you can have tags that are just private to that subroutine. So that's a little different there too. That's a local tag, but it's local to the function instead of local to the whole routine or to the whole program, which is what Allen Bradley's approach has been. Allen Bradley calls their FBs function blocks, which is the formal name, by the way, function block. That is the defined standard coding name in IEC 61131. They call theirs an AOI, and it cannot be edited online. It has to be edited offline and then downloaded, which means you're going to stop your processor. That can be a little bit awkward. It does not update everything automatically. There are some tricks there. You can edit in another program and then import it, and you can online edit that way. There is a trick there, but they never chose to make that editable online easily. Allen Bradley has a different way of doing things. I said 4 languages, primarily ladder, because instruction list is not considered a language that you would actually type in Allen Bradley. There's some tricks you can do in Excel to import things and do your mnemonics that way. Some of the words that Alan Bradley uses: aliasing is not done on these other platforms. You would have to map things, or you'd have to link a tag, but they don't call it aliasing. RPI, requested packet interval. Alan Bradley has a different way of scanning. So platform A, completely different scanning method than B or C. AFIs, right? Always false instructions. You can create an always false in these other platforms, but that's not what they call them. A no-op, which is actually a standard programming technique, and they just use the mnemonic no-op, no operation. Produce consume tags. This is sort of standard, but it's, again, particular to Alan Bradley in the way they do it with a PLC. They don't, that's a standard programming term, but the other PLC platforms don't use that. And their networking protocol standard is Ethernet IP, which some other people have created communication blocks and things like that for Ethernet IP. As a matter of fact, platform D, which was Omron, uses Ethernet IP as a standard. So it might be easier to communicate between Alan Bradley and Omron, for instance, than it would be Alan Bradley and Beckhoff or Siemens, because they use a completely different network protocol. So platform B, which I'm heavily involved in now, which is Beckhoff, they call all their little organization blocks POUs, program organization units. Within that, you can have programs, you can have functions, and you can have function blocks. Functions and function blocks are meant to be reusable, and that is pretty much a standard in, I would call it, classic software techniques. They use FCs and FBs a lot. You can have global and local or private tags. A lot of flexibility in how you want to connect your tags. And they pretty strongly recommend in the Beckhoff platform that you don't use any global tags. So they have these things called global variable lists, and they don't like you using those. Most people recommend against it, which is kind of, again, a modern software technique where everything becomes local to its unit. That can be very awkward when switching from Alan Bradley to Beckhoff, obviously, since everything is global and program-based rather than local or specific to a function. General memory area plus data blocks. That's the way pretty much Beckhoff works. They do have these things called GVLs, and you can just create a GVL and assign it to things. Actually, I'm reading this and it says general memory area plus data blocks. I don't think they have something specifically called a data block. So that may have been confused with the Siemens, which is what I was should have put in there. 5 languages common. All 5 languages are used in Beckhoff. I don't see much in the way of instruction list in Beckhoff, but I have a lot written on the other 4 languages. Instruction list is sort of like assembly language, and it's probably not going to be your first choice unless you're doing some really low-level bit-based stuff. And I would, again, probably choose ladder for that. But they're all used. Some of the other terms you would need to know for platform B and write into your spec, if that's what you're doing, is actions, methods, properties. Methods, for instance, are the same thing as procedures. If you do classical programming, that's a method is a procedure. Properties, you can establish a property and make your data private in that way. You can do gets and sets, and if you delete either the get or the set, it makes it either read only or write only. So that's another technique you just don't have on these other platforms. An interface, you can link things, blocks to each other using an interface and establish classes, which again is a standard programming method. If you were doing Python or C or something, people would know what a class was. And they use EtherCAT, which is a different Ethernet protocol, operates in a completely different way hardware-wise. So not something that you can use at all really in Alan Bradley. They may have a converter for it, but it wouldn't operate at all the same way that Beckhoff would. Siemens has evolved from the original Siemens, so you'll still see OBs, FCs, and FBs, function blocks and functions. Global and FC, FB tags and data blocks. And then registers, I said registers by function, not entirely true. So that's kind of a misprint. Registers in Siemens, you would still have all tag-based registers. and you would assign them either locally by function. So I could say this function block has temps and stats up in the declaration area, whereas if I went to Beckhoff, there is literally a text declaration area at the top of every routine, every program, every FC, every FB. So that's how you make things private. So that's why I put here temp, stat. Group is another thing you would have in Siemens that you wouldn't have in these other platforms. A group is just a folder. So you can create a folder and put your stuff in there, and it doesn't really make it private. It's just for human being organization kind of stuff. And again, their platform for communications and IO is Profinet, not compatible with Ethernet IP or EtherCAT, even though they're all Ethernet. They don't work exactly the same. And there's some fun pictures. I would say most of these pictures are from Beckhoff. The last one is not the SFC picture that I put in here. I put in my Beckhoff book because I wanted to show something that you really couldn't do exactly in their SFC charts on one page. It would have, you couldn't fold the stuff around and make it look like this. So I gave it as an illustration to have splits and jumps and these double bars and things like that. So that's a little bit of what those look like. I did not put instruction list in here. And again, instruction list probably wouldn't matter for most of these platforms, with the exception of possibly Siemens, if you had to do statement list in the new 1500s, which you can. So there's just a kind of a picture of everything. Mostly Beckhoff, but languages. So which language is best? This is something they wanted me to address in the control engineering webinar. Instruction list, again, they're even taking it out of IEC 61131. It's being what they call deprecated. It'll still be existent. It'll still be in the Siemens platforms, especially, but it's going to disappear completely from the standard, probably because you can do structured text and do much of the same thing that you do in instruction list. So if you need a text-based language, they're going to recommend structured text for everything. Very efficient. It's probably the cleanest way. If you want to write code, you can make it the fastest that way. However, very difficult for most maintenance people to follow, especially in the US. And the reason is that, again, people learn ladder here in school or definitely in plants, and that's what most of the stuff is programmed in, and it's graphical. So ladder logic is pretty easy to understand if you understand electricity. But for instance, I had some interns at Automation NTH that had a computer science background, and they did not understand ladder. They had a hard time adopting that because they didn't understand electricity, not something they learned in college, right? They didn't have to take electrical classes. So all of a sudden, all those relay coils and contacts and things and a timer block, they didn't know what this graphical language really was. They were used to programming in Python and C# and things like that. And so they had a hard time adapting to ladder. So I sort of understand where the people who like structured text, where that comes from. That comes from people like computer science folks and people who learned it in maybe even in high school. Structured text, familiar to computer coders, excellent for math and data manipulation. If you have to do really complex math, that's the language you would probably want to use. Can be difficult to maintain and modify. And I'm going to mention something else at the very end of this that is more of a reason that you might not want to use structured text. So difficult to maintain and modify. Some of it has to be compiled, turned into a different file. That's the way it works with Siemens. You compile it and then you download the compiled file, and then you have to kind of decompile it and look at it back in the editor if you want to monitor it. So that can be tough. Syntax can be different across different platforms. So in Beckhoff, we end everything with a semicolon. And in Allen Bradley, I think it's something different. I don't remember. I don't do a lot of structured text in Allen Bradley. I mostly use ladder, and I teach it and do little structured text that way. But honestly, Allen Bradley is just so widely AOIs and ladder logic that we don't do a ton of structured text. But I use a lot of it in Beckhoff. It just seems to lend itself more to that. Function block diagram. And I mentioned here common in process control and lab environments. I couldn't mention who uses function block the most, but if you've ever seen LabVIEW really lends itself to function block. Everything they do in there is little blocks, and you just glue them together. So very common in the process control industries and labs. Graphical, pretty easy to understand. Hard to do string manipulations or complex math for the same reasons as ladder. You would have to build blocks to do the complex math, put formulas in and things. It also may have a limited function set compared to ladder. I know in Allen Bradley it does. They don't have all the ladder instructions in function block. Function block kind of looks like ladder, except instead of attaching to a rail, you can just float blocks out in the middle of the space there. So your format can look pretty different there, but still pretty user-friendly. Sequential function charts, again, graphical, and I said easy, graphical and easy for maintenance personnel to follow for sequence debug. It's great for that. You can put it straight on your HMI and see where your sequence is. The problem is it can definitely take longer to code. Again, I teach Beckhoff, and when I do, the students usually end up hating SFC because it's kind of hard to get started. It's easy to understand what it's doing, but again, it's very particular how you build your steps and your transitions, and there's some kind of funny little N's and D's and things that you have to use, and you have to learn that language. So a little harder to code, but pretty easy to debug and easy to use. Program organization, that's another thing that is going to differ strongly. So here I put product A, right, Allen Bradley. You can see here the ladder 2, and then you can see system inputs. How are you going to arrange these ladders and things? And I do a lot of process work on the old platform here, and I would have things like tank 1 inputs, tank 1 sequence, tank 1 outputs, tank 1 registration, things like that. I'm also limited as the length of the names of all these. And then you see all these data files here where I've got some, the standard data files of B3 and T4, things like that. And then I went and made some new registers. And so I've got sim bits, sim words, sim reals. I can create new registers up to 255 in the old Allen Bradley platforms. In the modern Allen Bradley platforms, my program organization would be a little different. You can see here I've got a function block example kind of wedged in there. I've got different languages. I've got a machine task, and I actually run simulations in there. And then I've got a bunch of stuff in the main program, mostly for examples. Just examples of things for standard programming that way. Motion groups, completely different organization here. Your UDTs are down here in the bottom. So that's Allen Bradley's form of organization. You go to platform B, this is a picture of Beckhoff. And Beckhoff, you can see where I can make all these folders. And inside of the folders, I've got POUs, which are mostly functions and things. I've also created in my more elaborate program, I've got folders for instance, functions and function blocks. I'll keep all my function blocks together in a folder called FBs, and they would be under the POUs folder. So you can build whatever kind of structure you want here. I can put folder under folder under folder. I can't do that in the Allen Bradley platform, and I can't do that in the Siemens platform. So completely different organizational techniques. Visues here, these are my screen objects. I can put my HMI stuff right in my Beckhoff program. So I like Beckhoff a lot. Really good for learning modern programming techniques and structured text. It just tends to lend itself to that. So if you want to get into C and Python and things, Beckhoff is a great PLC to kind of back your way into standard programming. Old Siemens. This is, I put a lot of these windows here to kind of emphasize the fact that old Siemens is hard to manage all the windows. You may have 10 windows open at once, and the organization, everything's done from these online and offline manager sections, and you'd have all your OBs and FCs and things listed in here. System function blocks. Those are pretty much processor-based things that you don't have the ability to do much with. But you need to, they're already in the processor. Let me put it that way. Already in the processor, so you don't need to put them there. But if you look at it online, you'll see them. You look at it offline and you won't see them. There's a little bit of, again, the looking at the blocks on a real program here, node 10, and that's a kind of a collection of what's in that particular node. The modern Siemens platform, lots of folders and things. Again, I can make folders for program blocks and whatever. I can make subfolders, but it doesn't really separate them in the same way that it does with Beckhoff. Everything is still pretty much global in here. It's just for your own use that you would want to separate things. I've got something down there. It looks like at the bottom, it says other blocks. So I can create a folder, call it other blocks, and just tuck something in there so that I can find it later. Lots and lots of different folders already in there that you don't have to create, but a different organizational structure. So you can see here, completely different organization techniques, completely different data techniques and things like that. So that's stuff that you would need to be aware of if you're writing either a template or a standard for your particular brand of PLC. So when it comes to making rules for things, you have to take that into account. You can't just make a global statement that routines will be this. Well, maybe they don't even have things called routines in Siemens or Beckhoff. So you're making a standard and probably spelling it out for Alan Bradley. But if you're giving this to somebody who programs in Siemens, they may not know what you're talking about. The other thing that will differ is this is a typical program organization for machine control, something that I use a lot. And if you go and look at automotive manufacturers and packaging machines, things like that, systems integrators for machine control, you will see this commonly, right? You'll have a system routine of some kind, maybe they'll call it control, and it handles things like your auto mode, your manual mode, your system-wide functions, right? Maybe some of your safety. Inputs, debouncing and back checking and things like that would be in an inputs routine. Your mapping would be in an inputs routine. Control would be where your sequence was. You might have multiple control routines, and then you would have separate output routines, usually separate faults. And they would organize these so that the maintenance person could go to the outputs routine, say, why is my output not being fired, and trace it back through the other routines and make it really easy for the maintenance person or the manufacturing engineer or whatever. So it's organized this way commonly in machine control. You go to process control or utilities, things like that. A lot of times they use P&ID diagrams, process and instrumentation, right? Piping and instrumentation diagrams. So those assemblies have numbers. And if you're just looking at the number, it doesn't tell you much about what is that thing. But if you go in and you start looking at the tag names, and they have Z's or H's or things like that, all those H's and Z's in the tag name mean something completely different to somebody in process control. They kind of live and die by their P&IDs. So you might see a lot of numbered assemblies in a process control program, and they are particular to a section, a physical section of whatever the program's controlling. If it's tanks or pumps or things like that. And then the numbers actually have meanings also. They are defining an area and a sub-assembly, things like that. So completely different field. So your standard for process control would need to look very different than it does for machine control. Your alarms often are separated out. And again, it's so that if you have a particular alarm, you need to trace it. You would go to that alarm and it would probably take you inside of one of those P&ID assembly routines or sections or POUs or whatever. And then sometimes data acquisition is treated separately. They'll create separate routines for that so that the people who are dealing with SCADA can go find that information quickly. And that's just again, a convenient separation method. So that's a little on the organization part. What is a template, right? So a template, people ask about that. Can I use a template? Should I write a template? It's just a PLC program that's been structured and has some examples in it. So you could take one of your existing programs and strip out a lot of the process specific stuff, leave the stuff in there that is generic to all of your programming. You could leave that in there as an example, but you kind of need to put a lot of instructions up here. So I use this from one of my templates. Specifically, I said, input conditioning. Direct input addresses are not typically used in logic. So we're going to map everything. We're going to use status bits. And this example is from one of my books. So it uses these memory bits. It's kind of a generic treatment of it, but this might be alias to a physical address of some kind, like digital input card 1 would be alias to local 1 data something. And then on the output side, it might alias to a status register or something. And the aliasing is common in Allen Bradley. Some people in other platforms say they don't like it, they don't want to do it, but it's very common in a lot of the bigger plants. So like it or not like it, you have to live with what's there. You have to live with what the plant tells you to program. That's not usually up to the programmer. That's usually up to the plant or the integrator. So there on the left is, again, an organization. And this is the template. And then the organization might have samples of system inputs, outputs, faults, and inside of that, just one example of each rung that you might use. And then there's the same thing for Siemens on the right. This is the old Siemens, so not TIA portal. Software coding standards. I kind of addressed this in the control engineering webinar because that's a lot of what they wanted to get at. And some of the things I mentioned in here, for instance, tag naming conventions, I mentioned camel case, and some of the people asked afterward, what is camel case? Well, honestly, you can Google that and find it, but it's basically having capital letters in the middle of your lowercase letters. It is just a standard methodology for putting tags and addresses into any kind of software, right? So camel case, hyphenated camel case, Hungarian notation. That's a tag naming convention that Beckhoff recommends, where you put a lowercase b if it's a bool, a lowercase n if it's an integer, a lowercase s if it's a string. We don't do that, right, in Allen Bradley, because you can hover over the address and tell what it is, or you could see that it's a contact and you know it's a bool. So you really don't need as much of that. But in standard software, classical, modern software techniques, Hungarian notation is very common. So Beckhoff likes it. Allen Bradley, you literally almost couldn't use it. I mean, it wouldn't be necessary, and it would be very unusual if people saw Hungarian notation. File naming conventions. What are you going to call your routines? This could be really important if things are alphabetized, right? A lot of your lists are going to be alphabetized, so you might need to put like R01, R02 in your files. And then in other platforms, it just doesn't matter. They're going to want you to put FB if it's a function block rather than R01. Header files. I put this in here because this applies to standard software, and you honestly can't do this in most, ladder logic, things like that don't have header files. Global variable usage, definitions of that. Again, most classical software says don't use them at all. And then if you get into things like Allen Bradley, you're going to use controller tags. You're going to use some. Certainly your IO is going to be at the controller level. Exception processing. I put this in here again. I pulled it from a software standard, but you can't do that most of the time. If you have an exception in your processor, it shuts the processor down. You have a processor fault. There is no such thing as an exception, right? That's a programming error, major fault, shut the processor down. So you can't use some of these standard software techniques in defining a software standard like you do in standard software. Change documentation. This is important, but most PLC programs aren't going to be logged to GitHub and things like that. It's a nice idea to do all that, but practically that's not what machine builders and systems integrators usually do. They don't have time to do that. They don't often have multiple people working on a section of a program where they need to put it on GitHub and things, but they definitely need to log when changes are made, right? Maybe in the program itself or in a separate spreadsheet or something. Validation. They talk about this a lot in PLC programming for FDA applications. We have to do that in this country. So if you have validation requirements, you would need to write them into your standard. Unit testing. We don't do a lot of that, but yet in the Beckhoff forums, I see it all the time. You do unit testing on all of your modules. You know, that's just not the way things are done in an automotive plant. We don't do unit testing. We just write the code. We make it work according to our template. We debug it. We do a FAT and an SAT, and the system hopefully works when it ships to the customer and is written well. And if you're a large company, most of your programmers are going to write very good, bulletproof, solid code. So we don't do all the unit testing that they do in standard software. Libraries, they wanted me to address this. You literally don't have libraries in Allen Bradley. If you want to use a library, you need to just create a folder somewhere on your laptop and put your AOIs and your UDTs and your EDS files and whatever in there. And so a completely different technique again. But these are all things that they address in standard software coding standards. What is a library? So this is one of the differences I put in here. A library is a collection of functions, function blocks, instructions, DLLs, right, from a standard in computers, imported into a project to accomplish specific tasks. Some platforms have standard libraries built in. Backoff is what I showed here with manufacturer provided files or blocks. Siemens has a lot of this, a lot of libraries and things that you can import. Allen Bradley has none. So there are no libraries. You'd have to build your own and come up with your own methodology for that. B, Backoff required libraries. If you're going to program in Ladder, you will have the libraries that I showed to the right here, the standard, the system, and the module libraries you will have to have in there. If you use visualizations, you will have to have all the Visu libraries. If you want to do other special things, for instance, SQL, you will have to import those libraries and use them. So they are required. C, that's Siemens optional libraries. They have a lot of things you can import, or you can build your own function blocks to do the same thing. Terms to understand, I threw this in here as a time filler kind of in the webinar because I had to fill a solid 50 minutes and I didn't know what people knew already. So I put a standard hold-in circuit. I said, this is something you might put in your spec. Debouncing, this is all straight from my book. Right, so debouncing of sensors. You can find this all in the advanced PLC book and in my new book. Back checking of sensors, pretty standard thing to do. Again, in Allen Bradley, you would have a hard time doing something like a hold-in in structured text, right? So people say use hold-ins instead of sets and resets. You don't have any choice in structured text. You're going to use sets and resets, right? You wouldn't want to write some kludgy equivalent for a hold-in contact. Accumulators, these can be very important. Somebody might say, instead of using counters on this old platform, I want you to use entirely accumulators. And the reason is because Siemens counters suck. So that's where all that comes from. Accumulator, decumulator. I can build my own register and not have a byte-based Siemens counter that is done if it's not zero. That's one of the downsides of that. So to show people how to use that. Free running timer, just a tool that I use a lot. It creates pulses every, say, 1 second or whatever you want to put in here. Auto restart timer, I can use it for accumulation, things like that. Word sequence, state machine, very standard thing. You may tell somebody in your PLC standard, I want you to write all state machine code. I want you to do that in Ladder, or I want you to do it in structured text. All that means is we're establishing states for a sequence, and it's a 10, 20, 30 kind of thing. And again, I have a lot more explanation of bit and word sequence and state machines in my books. So if you're interested in that, you can read up on that. What is a function? A reusable section of code that allows variables to be passed in, creating an output result. This was one of the test questions I put in the control engineering. They do not have internal memory, do not use timers or one-shots inside a function, but the purpose of a function might be scaling. This function is from my Backoff here, and I use it for a standard output, right? So I put in, are you in auto or manual mode? What is your auto command and what is your manual command? Usually a push button. And what is your interlock? So I kind of built this as part of my Backoff class to explain what some of these things are. You can call that in Ladder or in structured text, it doesn't matter. And then what is a function block? And I put an Allen Bradley AOI here because that is really a function block. Reusable section of code, creating an output result. They do have internal memory. That manifests itself in different ways. If you're in Siemens, you're going to use a data block for your internal memory. If you're in Allen Bradley, you're going to have a UDT assigned to that AOI that is specific to whatever the tags are in there. So an example of a function block would be a retentive timer. If I don't have one in my platform, I can build one. It would be retentive, and that kind of explains why it has internal memory. Programming best practices. We're down to the last couple slides of the webinar. Keep logic simple. This is stuff you would put in your standard. You would say, I don't want to see big gnarly sections of code, one rung with 42 contacts and instructions in it. If you can't read it, you need to break it apart into smaller sections, because the person who does have to read it doesn't want to spend a lot of time admiring how fancy your code is. That's not the goal. If it has to be complicated for some reason, comment extensively, write lots and lots of comments. What I found interesting is looking in some software standards, they said minimize your comments. Don't explain things that should be intuitive to a programmer. Well, that depends, right? If you're a maintenance person, you're not necessarily a programmer. So things aren't as intuitive. So I say comment, if there's the least question as to whether something is necessary, go ahead and put a comment in there. It doesn't take much time. Use templates when available, and that solves a lot of your standards problems. If there's a template written, you're going to be following that template to the best of your ability. In my career, I've had to use, I don't know, probably 40 or 50 different templates from different companies. And I try to absorb something from each one. What's good about this template? What's bad? What's too detailed? So I put down here at second to the last, it says make code reusable as needed, but know when it's too much. I've seen some templates with just ridiculous reusable code in it that nobody can interpret. There is a such thing definitely as too much. Use local tags where possible. This again comes from the software standard software templates that I've seen online. I don't always do this. It just really depends. If there's a very standard way to do this in Allen Bradley, which is again my main platform. So I follow what the plants do. I don't make up my own rules on that. And they're not always local tags. They're going to use global tags for global things. So I go to, Beckhoff, and there's some well-known Beckhoff programmers that say no GVLs at all, no global tags. Everything should be local. You just can't do that in things like Allen Bradley, and you would be breaking somebody's rules if you did. So you have to be careful about that. Use descriptive, consistent tag naming conventions. Hungarian, if necessary, camel case, whatever you want to do. And this is where people asked what camel case was, and I had to put an answer, kind of write that in afterward for control engineering. And remember who your customer is, the person who has to maintain the code. It is not the bean counter who bought the machine. It is not the project manager who approved the machine. It's not the CEO of the company. It is the person who has to fix the thing in the middle of the night. So I'm going to make the code as easy as possible for that person. And that's kind of the way that works. Program maintenance best practice. Keep a master copy of the program in a secure location. I can't tell you the number of times that I have seen people that lost their program completely. They don't have a copy of the latest version. And when I say master copy, the problem is you'll have 4 laptops in a plant. Everybody has different copies of the program. And then something happens to the process. They have to go download it. And it's just a crapshoot as to which copy gets downloaded. So that's why we need a master copy. And a lot of times you'll have this on a server. You will check out the program and you'll go online with the processor, make your change, check it back into the server. So keep it a nice, secure place. I work a lot with a plant in Miami. We keep the master on the server, but the people on the floor do not have access to that master. So I even have them save it to USB and then put the USB in the cabinet hanging on a little peg inside of it. That's their standard, so that's what I follow. It's the next best thing. It's definitely better than having 4 laptops with 4 different copies of the program in it. So whatever works for you. Create a program naming convention with date tracking. Your file probably has a date already on it, so you can look at that, but I'd rather see it actually in the name of the program, certainly for Allen Bradley. It's just easy to do. So your ACD files, go ahead and put, 16 September 23 on it. Now that'll tell you when it was saved. This is the master copy for this date. Observe software validation regulations if required. I do a lot of stuff with FDA validated systems. You have to follow those rules. That's not an option. That's mandatory. Document your code changes outside of the program if possible. This is necessary with software validation anyway. So I just say, worst comes to worst, put it in a spreadsheet, keep track of why we made this major revision and why the old versions were saved somewhere else. Test your changes before implementing if possible. I'm guilty of not doing this in a lot of cases. If it's my program, I feel like I can just make the change and not test it, and I know what I'm doing. But in reality, in many cases, if it's something critical, you probably should test it somehow, simulate it, whatever. Consider cybersecurity and access to processors. PLC viruses and hacking is real. It's becoming a big thing nowadays. Real world stuff. Make sure that people aren't sticking USB sticks in the local computer, aren't going online with their computer that might have a virus on them, aren't compromising passwords and things like that. Other considerations, and this is where I got to the structured text thing. This is kind of the last slide of this presentation. Programming languages can cost extra on some platforms. Does the customer have the software? So in particular, this addresses the structured text question. It's nice to say, we want to use a lot of structured text. Why don't you use this? Well, one major reason for this is if I have Allen Bradley software and it has structured text in it, that doesn't mean that the customer has that software. If most of what they do is ladder, they not only don't know how to use structured text, they may not have the plugin that allows you to open the code and change it. So that's another reason that we don't use a lot of structured text, in particular in Allen Bradley. If I'm doing Siemens, I'm doing Beckhoff, different story, there's a good chance that they would have the software for the Siemens, and for the Beckhoff, it's just included. And as a matter of fact, most of your code is probably going to be structured text anyway. Text-based languages may be harder for maintenance to understand, quickly solve problems with cross-reference, etc. Same thing for pointers and indirect addressing. If you're using a lot of indirect stuff, arrays with pointers, that might make it pretty tough there. And then different industries, again, reiterating what I said earlier, use different methods. One size does not fit all. The language used in process control, the PNIDs, do not apply to machine control. Many people in machine control don't use that. So that's just something to keep in mind. So that's kind of everything from the webinar, the previous webinar. The next webinar, I'm planning on October 7th. I may have Phil Scruggs here again. He does a whole lot of stuff with microprocessors, so I may have him on, but right now the topic is unknown. At this point, I'd say a couple people on here. Is there anybody who has any questions about anything that we've talked about here? Okay, well, on that note, I'm going to go ahead and call it a day here. Again, next webinar, October 7th. If you're interested in the Automation Academy, lots of stuff going on there. I've got some new people working on stuff, always coming up with new content and putting it on there. Have some new videos coming out. Just created some on PID programming. So especially particular to Allen Bradley, there's a very good explanation of how PID works. And then I did put the PID instruction and went through a lot of detail on how it's used. And also there is a software program. It's I think version 31. So if you don't have Allen Bradley version 31, you wouldn't be able to use it. But I even put the HMI program in there, Factory Talk View ME, I believe version 11. But there's also a video of it, so you can see how it's done, and you could probably even build your own using the video. So that's it for me. Thanks for attending, and we'll see you next time.